All right, this is section 4.1, and in section 4.1, we're going to introduce exponential functions. So I put a copy, a blank copy of these pages under files, so you might print those out before you watch the rest of this, because I am just going to use the graph shown to graph these. Now over here on the side, I'd like you to take some extra notes. All right. So all the functions on this page are of the form f of x equals c times a to the x, okay, or y. These functions say y. So the a here is the base of the exponential function, and then x is the variable, obviously. Now this extra c in front here is what we call the initial value. All right, c is the initial value. This is what we call the y-intercept as well. All right, so it's the initial value, because if we were to plug 0 into the function, we would get a to the 0, which of course is 1, and then 1 times c. So when x is 0 on the y-axis, we're always going to get a value of c. So all of these equations, you'll see where to place that c value on the y-axis. Now exponential functions have two basic shapes. First, we have exponential growth, and you can look at the equation and tell whether it's an exponential growth. So it's a growth if a is greater than 1, right? If the base of this exponential function is greater than 1, okay, and the exponent is positive, right? So we're looking for positive x's greater than 1. Then we're going to get an exponential growth. So exponential growth, if I were just to graph y equals a to the x. So I'm not putting the c on there, all right? So the c is understood to be 1, okay? So all of our exponential growth equations are going to go through 0, 1, and they're going to grow exponentially to the right, and then they are going to decrease to 0 on the left. They're all going to have this basic shape. Okay, and all of our exponential functions will have a horizontal asymptote at y equals 0. So what's the difference, okay, between our different exponential bases, like 2 to the x, 5 to the x, 10 to the x? So let's say this is 2 to the x here. Okay, the higher the base, the faster it's going to grow. So 5 to the x, for instance, okay, is still going to go through 0, 1. Because if I had 5 to the x here, if I plug 0 into the x, 5 to the 0 power is still 1. So we're still going to start at 1 here. It's just going to grow faster. All right, so the higher the base, the faster it grows, or the closer to the y-axis it is. And it's going to decrease faster as well. Okay, so this is 5 to the x. So 10 to the x, I didn't really leave myself room, but it would just be tighter, okay, to the y-axis there. Here's your exponential growth, when the base is greater than 1 and the exponent is positive. So we have another basic shape here, and that's exponential decay. So exponential decay is, you can tell by looking at the equation, if the base a is between 0 and 1, right? No negatives. The negative sign is a reflection. We're not going to worry about those. Right, so if the base is a fraction or a decimal between 0 and 1, okay, or if the exponent is negative, because negative exponents cause a decay as well. So if I were to do y equals 1 over a here to the x, we're going to get an exponential decay. So exponential decays also go through the point 0, 1. Because if I were to plug 0 in for x, I would get this fraction raised to the 0 power, which is 1. So this graph is going to go through 0, 1. Now the decay, it's going to be the reflection of the growth here. right? So it's going to be a decreasing function. And again, if this is 1/2, 1/5 to the x would decrease faster, 1/10 to the x, again, even faster. So we kind of mentioned that negative exponents and fractional bases are the same, and I want to kind of show you why. So say we had 2 to the negative x, right? This would be an exponential decay. Yes, the base is greater than 1, but we have this negative exponent. So we can use our rules of exponents to change what this looks like. And if I wanted to make this exponent positive, I would move it to the denominator. So I would have a 1 on top and a 2 to the x on the bottom. Now I'm going to do a little bit of fancy algebra here. This 1 over 2 to the x is equal to 1 to the x over 2 to the x, right? Because if you raise 1 to any power, you still get 1. And then I can factor out the x. So I get 1/2 to the x power. So you can see how the negative exponent really turns it into a fractional base, right? They're the same things. So we're going to practice graphing these, right? So when we graph them, you need to make sure your y-intercept is correct, and then you need to make sure you have a growth or a decay. And then we're going to practice graphing them with a vertical shift in them as well, right? So we'll talk about what that does when we get to it. So first example, okay, we have 4 times 2 to the x. So the base of the exponential is 2, the exponent is positive, and we have an initial value of 4, right? So if I were to do like a table here, x, comma, or x and y, if I were to plug 0 into this function, 2 to the 0 is 1, 1 times 4 is 4. Okay, so it's going to go through 0, 4. If I were to plug 1 in there, 2 to the first power is 2, times 4 is, 2 to the first power is 2, 2 times 4 is 8. So it's already going through 1, comma 8, right? So if I were to put a negative 1 in there, right, I have 2 to the negative 1 power. Well, 2 to the negative 1 power is the same thing as 1/2, because we're moving that 2 to the denominator, and so then half of 4 is 2, so it's going to go through negative 1, 2. So there will be some questions on your homework of filling out a table of values, so just calculate them, right? But this one's going to be a growth, right? This is a growth, and the initial value is 4, and since there is no vertical shift here, we know the asymptote is going to stay at 0. All right, so I'm going to put the initial value on here at 4, okay, and then I'm going to draw a growth through there. So I do know that it goes through 1, comma 8 because I figured it out, and then negative 1, comma 2 here, all right. But I know that the asymptote is at 0, and we're going to draw a growth shape through those values. Right? All right, so here, next. Okay, y equals 5 times 2 to the x. The base is 2. The exponent's positive, so I know this is a growth. Right? I know the initial value is 5. Okay. And then the asymptote's not moving on this one either, right? So I'm going to kind of eyeball this one a little bit more, right? Put the initial value at 5, the asymptote at 0, and then I'm just going to draw the growth shape through this point. So it's going to grow exponentially on the right, and it's going to decrease to 0 on the left. On the bottom here, okay, we have y equals 4 times 1/2 to the x. So the base of this exponential is a fraction between 0 and 1. Right? And the exponent is positive. You just need one or the other to be a decay. So this is a decay. And the initial value is 4. Right? We don't have a shift on this one either. We will get to those that have shifts, but this one doesn't either. So I'm going to put the initial value 4 there. We'll put the asymptote at 0, and I'm going to draw a decay, okay, a decreasing exponential function through that point. right? 2 times 1/2 to the x. Again, the base here is a fraction. The exponent is positive, so this is a decay. The initial value is 2. So I'm going to put the y-intercept at 2 and the asymptote at 0 and draw a decay function through that point. Right? So just make sure you can tell the difference between a growth or a decay, and you'll probably be over halfway there. All right, so the next graphs, this page of 4 here, has some extra numbers. Okay, so this 2 is the base, right? This 3 is the initial value, and this plus 2 is a vertical shift up, right? Vertical shift. And so this is going to tell us where to put the asymptote, right? So I'm going to start this graph off. Okay, instead of putting the asymptote at 0, I'm going to put it at 2. Now this initial value of 3, is not the y-intercept in this problem. You have this initial value is how many units above the horizontal asymptote it's going to cross the y-axis. So since the initial value is 3, we're going to go 3 units above the asymptote here for our initial value. Okay. Now this one also has a minus 2. This minus 2 is a horizontal shift. And because it's negative, we're going to shift it to the right. So we're going to shift right 2 as well. Right? So the asymptote here gets shifted, but you don't see that, right? Because it's not going to make any change. But this point needs to go to the right 2, right? So our initial value is basically 2, 5, if you will, right? And then we're going to draw our growth shape after all those shifts. So the growth shape comes to 0 on the left and then increases to infinity on the right. All right, here we go. Another one. This minus 2 is a shift down. Okay, and this minus 1 is a shift right. And this 4, the initial value is how many units above the asymptote we're going to put our point, right? Notice that the base on this one is a 1/2, so we're going to do an exponential decay. So this shift down tells you exactly where to put the asymptote. Okay, the horizontal asymptote is at -2 this time. So I'm going to draw the asymptote first. Okay. And then the initial value is 4. So 4 units above the asymptote is the y-intercept. So 4 units above -2 lands at +2. But that initial value also needs to get shifted before you draw the graph. So since it's x minus 1 here, I'm going to shift this point to the right 1 and put the initial value point here. To the right 1 and up 4 from the asymptote. So because it's a decay, I'm going to make sure I draw the decreasing exponential function through that point. All right, there's a lot in there, I know, but it's using your graph transformations, all right? So these big -2, this -2 is occurring on the outside of this exponential function. So any transformations that occur on the outside are vertical shifts up and down. Okay, this -2 is in the exponent inside the function, and so those are your horizontal shifts left and right. This initial value really is a stretch, if you will, a vertical stretch. But just remember this tells you how many units above the asymptote you need to put that point. Okay, so let's go ahead and do the bottom 2. All right, the bottom 2 ask you to write an equation for the function. Right, so we're looking for a function. C times a to the x plus k, if you will. All right. So this is our vertical shift. We don't have a horizontal shift because it looks like it's shaped here. All right. We could solve. They're not going to do that to you. All right. And then here's our initial value. So it looks to me like the asymptote here is at 1, right? Because this function is decreasing and it's not going to go below 1. So that tells me the horizontal asymptote is at 1, right? So I already know the k value. So I'm going to go ahead and fill that in. So now I have c times a to the x plus 1, if you will, right? Now what's the initial value? Okay, how many units above the above the asymptote is it crossing the y-intercept? And so it's crossing the y-intercept at 2, and that's only 1 unit above the asymptote. And so I know the initial value is 1, right? So I get y equals, I'm not even going to write it, because 1 times a to the x is a to the x. So now I have a to the x plus 1. So what we really need to be able to find is what is the base of this exponential function, right? So don't take the y-intercept, take some other point on this graph. And it looks like it's crossing a grid line here at 1, 5. Right? So this exponential function should go through the point 1, 5. So if I plug 1 in for x and 5 in for y, I should be able to solve for a. All right? So I get 5 equals a to the first power plus 1. Right? So if I solve this equation for a, I just need to subtract 1 from both sides, and the exponential base is 4 here. So my equation that I'm looking for is y equals 4 to the x plus 1. Right? And a shift up, no shift to the right or left, and the base of this function is 4. It is best to find this point at where it is at 1, if possible, because that makes this equation the easiest one to solve for. So let's go ahead and look at the next one. Okay, growth, right? It looks like it's not going to go below -2 here. So I think the asymptote is at y equals -2. All right. So I'm going to go ahead and start with an initial value times a to the x minus 2, because that's where the asymptote goes. So what is the c value? How many units above the asymptote does the graph cross the x-axis? Or, sorry, the y-axis. So it's crossing the y-axis at -1. The asymptote's at -2. So again, that initial value is only 1. Right? So I know c is 1 here. All right, so I'm going to put, now I have my equation a to the x minus 2. So I have to solve now for what the base is. So look at where it is at 1. Right? We're going to find 1. It goes to the point 1, 1. Right? So if I take this point x, y and plug it into my equation, that'll allow me to solve for a. So I have 1 equals a to the first minus 2. Right? So to solve for a here, I'm just going to add 2 to both sides, and I get a to the first equals 3. Right? A to the first, or just a, same diff. Right? So I know that the base of the function is a, the initial value is 1, and the horizontal asymptote is at -2. So therefore, I get an equation 3 to the x minus 2. So the y-intercept is going to help you find the c value, and the point at 1 is going to help you find the base. And that's how you're going to find these equations of these exponential functions. Notice both of these examples, right, are increasing. So it should be an exponential growth. So our base should be greater than 1, and they were. Right? So make sure that checks out. All right, so I have some other ones to look at here. 4 more here. Okay, So this graph here, -3 times 2 to the x. Notice there is no vertical shift, right? So it's like +0. So the asymptote is at 0 here. And they've only given you the bottom of the graph, and there's a reason for that, right? Is this a growth or is it a decay? Look at the base, right? The base of this function is greater than 1 still. Yes, we have a -3 out here, but the base of this is still greater than 1, so we are looking at a growth graph, right? Now, what's the initial value? Okay, that's where this comes in. So now the initial value is going, because it's -3, it's going across the y-axis 3 units below the asymptote. So the initial value here is -3, right? So what's happening here with the -3? Let's take the, let me cover up the negative sign. This is like 3 times 2 to the x with a growth. So if I were to graph it without the minus, it would look like it's growing, right? It's be an increasing function. That negative sign reflects it. So you need to reflect the growth, right? So I'm going to kind of draw a dotted growth function up here. So if I were to reflect that shape vertically here, that means on this side it should be approaching 0. On this side it should be going to -infinity, right? Because we're mirroring the growth shape below the x-axis. We don't want to draw a growth here because then we're crossing our asymptote, right? It's a reflection, right? So the initial value is -3. It is still a growth, but it's a reflected growth, right? So it's going to go to 0 on the left and to -infinity on the right. All right, here we go. Next, 3 times 1/2 to the x. So here's our base, right? This tells you it's a decay. So our graph should be decreasing. There is no vertical shift, so the asymptote's at 0, and the initial value is a +3. So 3 units above the asymptote is where we need to draw that initial value. So the asymptote is at 0, the initial value is 3 units above that, and we need to draw a decay through that point. All right. Same thing here, okay, decay, initial value 4, the asymptote is at 0, so asymptote at 0, initial value at 4, draw a decay through that point. Right. Here, we have -4 times 1/2 to the x. So technically this is a decay, and this is an initial value of -4. Okay, there is no plus or minus, a constant here, so there is no shift. So I know the asymptote is at 0, right? I know it's a decay, but we're going to have to reflect that decay because of the minus sign. So the initial value is -4, right? But we don't want to draw a decay here. We want to reflect the decay. So if it was just 4 times 1/2 to the x, it would look something like this. Okay, here's our decay function, right? It decreases. So if I were to reflect that over this asymptote, the graph should approach 0 on the right and then go to -infinity on the left. Right? It's a mirror image of that decay graph. All right, so that's the first part. How do you graph exponential functions? It's just a matter of finding whether it's a growth or a decay and finding where the asymptote is, okay, and that initial value. All right, next part of 4.1 is an application of how we're going to use these exponential functions. So I posted a picture of a bunch of word problems that I would like to work through with you. So these word problems are using what's called a compound interest formula. It's a really common exponential function, right? So the compound interest formula, looks like so, right? A equals P times 1 plus R over N raised to the NT. Right? So there's a lot of variables here. So what do these stand for? Right? A stands for an amount. Okay. This amount is after the interest has been added. Right? So the amount in the account after interest. P stands for principal. This is the initial investment. Okay, so you're going to put $100 in the bank. You're going to let it accrue interest. That interest can be added, and you get the amount after a certain amount of time. So this is the initial investment. All right, R stands for the interest rate. So interest rates are usually given to you as a percentage, right? 8%, 12% interest, 3% interest. But when you plug this interest rate into the equation, you need to make sure you write it as a decimal. Right, so for example, right, if you have a 5% interest rate as a decimal, it's going to be 0.05, right? 5%, 5/100ths. Okay, R. Right, N is our new variable here. N stands for the number of compounding periods. How often is the interest, compounding periods. How often is the interest being added to the account? All right. So interest is compounded annually, semi-annually, monthly, weekly. So you got to know what all those different values are. So if it was annually, right, then the number of compounding periods in 1 year is 1. The interest is only going to get added to your account once. If the interest was compounded semi-annually, that means N is 2. The interest will be added to your account twice in 1 year. The next semi-annually, quarterly. Sometimes we have quarterly interest payments. And so quarterly means it's going to be 4 times a year, right? They can compound the interest monthly. And so obviously there's 12 months in a year, okay? Weekly, sometimes you get weekly interest payments, and so there's 52 weeks in a year, so N would be 52. And then daily, all right? So you kind of have to be careful with the daily. I'm going to go ahead and use 365 days in a year. Of course, this year we had 366 because it was a leap year. Some financial institutions, however, use 360. And I don't know if that's, they're taking into account all the federal holidays there are, but you want to make sure that you're using the correct N value when they say daily. Is it 365? Is it 360? What exactly do they mean there? All right, so that's what we're going to plug in for N. All right, now there's one, and then the N is going to go in 2 different places, right? One, we're going to divide the interest rate by N, and then the other N is going to be multiplied times T. What is T? Okay, T is time in years. All right, so why do we divide the interest rate by N? Okay, so if we had, let me make it easier on myself, okay? If we had a 12% interest rate and it was compounded monthly, that does not mean we're going to get 12% every month. What the financial institution is going to do is it's going to give you 1% every month. And so 1% every month is going to add up to 12%. Now when we compound the interest, you're going to get interest on top of your interest. And so say the first month you got you got like 10 cents in interest. So the next month you're going to get interest on your initial investment plus that 10-cent interest, right? So you're going to get like 11 cents the next month in interest. And so it keeps going up, okay? It keeps adding. So the interest rate divided by n is telling you how much interest you're getting per period, okay? So that's the annual interest rate divided by how many times it's being compounded, right? Now this exponent is how many total times it's being compounded, because if it's monthly for 3 years, you're getting interest added to your account 36 different times, and that's what this exponent represents, right? So I have a few examples of using this compound interest equation, right? So I'm just going to flash them up here, okay? Because I really don't want to write them down, right? So say here, okay, number 1, let me zoom in. Find the amount that results from an investment of $8,500 if it's invested for 3 years at an interest rate of 4.25%, and the money is compounded monthly, right? All your important information is here. So first, find the amount. That means we're looking for A, okay? A is what? We don't know, right? The initial investment is $8,500, so P is going to equal $8,500. The interest rate is 4.25%, but if I want to write 4.25% as a decimal, I need to move that decimal over 2 places to the left. So inside the equation, I'm going to use 0.0425, right? So to go from a percent to a decimal, you just move the decimal place to the left 2 times, right? N is the number of compounding periods. So this one says that the money is being compounded monthly, right? That's 12 times a year, so N is 12, right? What's the time frame here? Okay, how many years are we going to let this investment grow, right? It's invested for 3 years, so T is 3. So if I plug all these numbers into the formula, I will be able to calculate how much is in the account. So I'm just going to write down that formula again. 1 plus R over N raised to the NT. Okay. So I have A equals, principal is $8,500 times 1 plus the interest rate, 0.0425, divided by 12, because it's compounded monthly, right? And then up here in the exponent, we're going to do 12 times 3. Okay, 12 times a year for 3 years is 36. Right, so you are going to need a calculator for this. Now, when you plug it into the calculator, you want to be very, very careful. Right, so I do it in steps. I do the parentheses first. All right, 1 plus 0.0425 divided by 12. Right, and I figure out what that decimal is. Right, so I get 1.0035, okay, 667. Now I'm going to keep that. Now in order of operations, we do parentheses first, right? And then in order of operations, after parentheses comes exponents. So I need to do the exponent before I multiply times 8,500. So this decimal is inside the parentheses. I need to raise that to the 36th power. So go ahead and just click your caret, right? That raises to a power. Notice your calculator is going to take the previous answer, okay, raise it to the 36th power and hit enter, right? So now we get a new decimal, 1.135, right? And so now we have done the parentheses, we've done the exponents, now we're going to do our multiplication. So multiply that answer times 8,500, and we get our answer 9653. Now, how many decimal places do we use? This is dollars and cents, guys. Right? We have how many cents? Well, cents is 2 places after the decimal. So I have 0.696644. So how many to the nearest cent? Right? So after 69 cents, I have 664. So this is greater than half, right? So I'm going to round this up. So 69 cents needs to be rounded up to 70, right? So to the nearest penny, we're going to get $9,653.70. So make sure you're rounding your answer to the nearest penny, all right? To the if this was like 325 here, 0.69325, okay, that 325 would have been less than half, so I would just left it at 69 cents. But as it is, I needed to round that up to the 70 cents, all right? So let's go ahead and work the next one. Or not the next one. Let's do number 3. Okay, this number 2 here we're going to do in the next section, all right? Because it says it's compounded continuously, and so we needed to use a separate equation if we're compounding that interest continuously. So we will look at that one in 4.2. Let's look at number 3 instead. All right, so number 3 here. Find the principal needed now to get $850 after 3 years at 5.5% compounded quarterly. So it's like planning ahead, right? Say in 3 years, you know you're going to need an extra $850. Well, the question is asking, well, how much principal do you need now to invest it and get $850 in the future? Okay, so this $850 is after interest. So the amount this time is $850, and we're looking for the principal. Okay, how much we need to invest, right? Find the principal. That means we don't know what it is, right? So then we need to kind of figure out what R, N, and T are. Right? So R is the interest rate as a decimal. So 5.5% is 5.5%, right? So if I change that to a decimal, I'm going to move this decimal place to the left 2 times, and so I'm going to get 0.055, right? Twice, right? 0.055 is our interest rate. N is the number of times it's compounded, right? So this one says it's compounded quarterly. Quarterly means 4 times a year. So I'm going to plug 4 in for the N value. How much time? Okay, how many years? Okay, it says after 3 years. All right, so I'm going to plug those numbers into the formula. I'll rewrite it for you. Here's our formula. Okay, so I have 850 equals P times 1 plus 0.055 divided by 4, right? The interest rate divided by the compounding periods raised to the 4 times 3, N times T, right? So I need to solve this for P. So I'm going to figure out what this number is, okay? And I'm going to divide it here. And I think it's easier to calculate this decimal and divide by the decimal than it is to kind of divide by that fraction with an exponent, all right? So I'm going to figure out what this is first. So inside the parentheses first, right? Parentheses and then exponents. So we're going to do 1 plus 0.055 divided by 4. That'll get me what's inside the parentheses. Then I'm going to raise that to the 12th power because 4 times 3 is 12. And that's going to tell me what that decimal is, all right? So right now, I have 850 equals P, excuse me, times this decimal. You don't want to round this decimal at all, or else you're going to get off by a couple pennies, and it's going to be frustrating because you have the right answer, but you're off by a cent or two, and it's going to count it incorrect. So don't round that decimal at all. So if I wanted to solve for P, I'm going to divide both sides by that decimal. All right, so I'm dividing both sides of this equation by 1.178. So there's an easy way to do this on the calculator so that you don't have to retype it. All right, we're going to do 850 divided by that decimal. So type in 850, and then go ahead and hit your division symbol, and then I can pull this answer. All right, so answer is located above the negative symbol. It's in blue. Right, so if we hit second and then the negative sign, you can see on your screen it says 850 divided by the answer. So it's going to do 850 divided by this decimal. And the calculator is not going to round it at all. So go ahead and hit enter, and that'll get you the exact dollars and cents. All right, so P to the nearest cent, we have $721.5202412. So we have 52 cents right now. After the 52 cents, we have 0.02412, so that's less than half, right? So I'm going to go ahead and leave it at the 52 cent. I'm not going to round it up. So I have $7.21.52, right? That's how much we should invest today to get $850 in 3 years, right? So that's a pretty large investment, but it is a free 130 bucks, okay, in interest. And so if you put that in the bank today, under these conditions, in 3 years it'll grow to $850, right? So one more, okay, I'd like to look at number 4. Excuse my demonstration, my high-tech demonstration process here. All right, number 4. How long will it take $2,000 to triple in value if it earns 6% compounded continuously? Here's that continuous. Let's compound this money. Let's go quarterly. Let me change it just so I can show you this example. All right, because the compound interest only works if it's not continuous. All right, so we want to know how long will it take $2,000 to triple. So how long is asking how many years? Okay, how many years will it take? Right? So we got to know what the amount is, what the principal is, right? The interest rate we have to know, the compounding periods we have to know. It's the time that we're looking for, right? So it's the time that we're going to leave as a variable in our equation. So we're going to invest $2,000 and we want it to triple. So we want the $2,000 to grow to $6,000 basically. So $2,000 before interest is the principal. The $6,000 is the amount we want after we've added all the interest, right? So that's how we triple our money. So the interest rate is 6%. If I change that to a decimal, we're going to get 0.06. Right? I changed the compounding from continuously to quarterly, so n is 4, and then we're solving for time. So again, I'm going to write down this equation. Right? And we're going to solve for t here. All right, so we get A is 6,000. The principal is 2,000. 1 plus 0.06 divided by 4 raised to the 4t. You know, I took these problems off of the pre-calc, and obviously the pre-calc covered a little bit more material before they did these financial models. Just bear with me here. I don't think you're going to have any like this on your homework, but I don't want to leave this problem unsolved. Right? The exponent here, this is an exponential function, a true exponential function, because we have a variable in the power here. So the first thing I want to do is I want to divide by 2,000 to get that parentheses by itself. Okay, so 6,000 divided by 2,000 is 3. And then I have 1 plus 0.06 divided by 4 raised to the 4t. Right? Now what we do here, okay, I apologize, but if this is beyond your understanding, you can stop listening at this point. Okay, I really am sorry, but I want to go ahead and show you when the variable is in the exponent, we have to ln this function. All right, so I'm going to ln both sides. All right, and so I get ln of 3 equals ln of this. Now the reason why we ln the function is because that brings the power down. So just go with me here. I get 4t times ln of 1 plus 0.06 divided by 4. Okay. So what I'm going to do is I'm going to divide by 4 here. Okay, so I'm going to get ln of 3. Ln of 3, parentheses, divide by 4. I'm going to write down that decimal. And then I have, since I divided by 4, it cancels. Now I have the t times ln of this number. Okay, this is just a number, so I'm going to go ahead and type that in and figure that out. So ln of 1 plus 0.06 divided by 4 is another decimal. Right. Let me put it in parentheses. So if I wanted to solve for t, I just need to do divide by this 0.014 number on both sides. Okay. So I'm going to use a calculator here. It is kind of nice. You can use your direction arrows to grab it. So I need to do, I'm going to scroll up. I'm going to grab that 0.27 decimal and then divide it by, I'm going to go up and grab that 0.014 decimal, and then hit enter, and that's going to be 18.447. So this is what time is. Okay, basically it's going to take 18.5 years for the investment to triple if you're only getting 6% interest. All right. So I apologize for the advanced doing ln when you haven't even learned ln, but it is an interesting question. But if you can pull these values out of the word problem and plug them into this formula, I'm sure you will be fine on section 4.1. Have a great day.